Hello, Summer 307 students, and it is my pleasure to welcome you to this video. So in this series of videos, I'm going to be talking about a inferential statistical test known as a factorial ANOVA. So last week, we talked a lot about a one-way ANOVA. And whenever we hear the term one way in the context of statistics, we are referring to an experiment where we are looking at the effects of one categorical independent variable on a continuous dependent variable. And we can either have a between subjects design or a within subjects design. So with a between subjects design, we are comparing at least 3 different groups of people. And what varies between those 3 groups of people is the levels of our independent variable, right? So one of the examples I gave last week of a between subjects design that would utilize a one-way ANOVA is having people study a passage, right? So looking at people's memory for a passage, that's our continuous dependent variable. And then the variable that's manipulated is the particular study instructions that they're given, right? So in one condition, in one level of our independent variable, participants simply read the passage. In another version or another level of the independent variable, participants read the passage and then are tested on the passage. And then in our third and final level of our independent variable, the participants read the passage and develop a mnemonic device to remember its contents, right? So our categorical variable is study method with 3 levels, either reading plus studying, or reading plus a mnemonic device, right? And then we look at memory scores to see which group did best, right? So that's kind of a classic between subjects ANOVA design. We can also do, so I should say, with a between subjects design, we're comparing 3 different groups of people at the same time on the same continuous dependent variable. With a within subjects design, obviously it's an ANOVA, which means we have at least 3 levels of our independent variable, right? And we'd also have that continuous dependent variable. So we could use the same exact parameters that I just gave for our between subjects ANOVA, except we're comparing the same group of people at different points in time, right? So maybe I give the same group of people 3 different passages. And for one of the passages, they simply read it. For another one of the passages, they read it and then are tested on it. And for the third passage, they read it and then create a mnemonic device, right? So in that case, we are comparing their memory for those 3 passages under each of those 3 different conditions, right? So with between subjects designs, we're comparing 3 different groups of people at the same time, whereas within group designs or within subjects designs, we're comparing the same group of people at different points in time, and each person participates in all 3 conditions or all 3 levels of the independent variable. Okay, so that's a quick review of the one-way ANOVA and a between subjects versus within subjects design. Okay, this week we are going to learn about what are called factorial ANOVAs. And a factorial ANOVA is used when we have 2 or more categorical IVs and we're seeing how those independent variables affect the same dependent variable. Okay, so now we're going to go through some examples of what a factorial design might look like. Okay, so let's suppose that our research question is, what is the best type of peanut butter and jelly sandwich? Okay, and we have two different independent variables. Okay, we have one type of peanut butter. Okay, and our two levels are crunchy versus creamy. Okay, and then our second independent variable is type of jelly, and we're comparing grape versus strawberry. Okay, so in order to conduct a factorial ANOVA, we need to look at all of the different possible combinations of our independent variable. Okay, so like I said, our independent variables are type of peanut butter, and our other independent variable is type of jelly. Okay, and our dependent variable is going to be rating of deliciousness on a 1 to 10 scale. Okay, so we're going to use a Likert scale, also known as an interval scale, to formally assess the level of deliciousness of the sandwich, right? Okay, but like I said, we need to look at all possible combinations. Okay, and one really important thing to understand is the particular notation that we utilize whenever we're talking about factorial designs. Okay, so the first thing to notice is that we have two numbers. Okay, so the number of numbers, okay, or are going to tell us how many independent variables we have. Okay, so how many numbers are there? Well, there's two numbers. So that says we have two independent variables. Okay, and then what each number represents is going to be the number of levels for the independent variables. Okay, so we know that there are two numbers there total. So we have two independent variables, and the first number refers to the number of levels in IV1, and the second number refers to the number of levels in IV2. Okay, so we have two independent variables, and each has two levels, right? So we have IV1 is peanut butter, and the two levels are crunchy versus creamy. And the second independent variable is jelly, and it's grape versus strawberry. Okay? So another thing we can tell right away from this notation, okay, is the total number of groups that we have. Okay? And we can figure this out simply by multiplying. Okay, so if we take that 2 and multiply it by the other 2, that tells us that we have 4 different groups, and each group is going to have its own mean. Okay, so when we are utilizing a factorial design, okay, we can test for 3 things. Okay, and the first thing we can test for each independent variable is something called a main effect. Okay, so what that would mean, for example, let's say we wanted to look at peanut butter by itself. Okay, so let's just pretend for a moment that we were conducting a regular experiment with just one independent variable. Okay, so let's say our only independent variable was peanut butter. Okay, what we would be looking at if we were looking at a main effect of peanut butter is, regardless of jelly flavor, do people like one type of peanut butter better? Okay, so regardless of the type of jelly, whether it's grape or strawberry, do people prefer crunchy peanut butter or creamy peanut butter? Okay, and another way of thinking about this, if we look at our table, are the overall means for crunchy and creamy peanut butter different? Okay, if we were to completely ignore that jelly independent variable, would the levels of deliciousness for crunchy versus creamy peanut butter differ? Okay, and we can also look for a main effect of jelly. Okay, and in this case, we would say, regardless of peanut butter type, do people prefer one flavor of jelly over another? Okay, so regardless of whether the peanut butter is crunchy or creamy, are the overall means for grape and strawberry different? Okay, and the last thing we can test for whenever we conduct a factorial ANOVA is we can test for something known as an interaction. Okay? So don't worry about this quite yet, but we're going to get there really soon. Okay? So for right now, just hold that in your mind and we'll return to it in just a second. Okay, so again, anytime we use a factorial ANOVA, we can test for a main effect of IV1. So ignoring IV2, is IV1 related to our dependent variable? Okay. We can test for a main effect of IV2. So ignoring IV1, is IV2 related to our dependent variable? Okay. And lastly, we have something called an interaction. So whenever we test for an interaction, the question that we're asking is, does the effect of independent variable 1 depend on independent variable 2? Okay? So I'm going to walk you guys through an example that will hopefully make this a lot more clear. Okay? All right, so let's consider this psychological study that was actually conducted. So this comes from an actual research article. Okay, so in this particular study, one group of males saw a woman's photo on a white background, and a second group of males saw the same photo, so they saw a picture of the same woman, okay, but they saw it on a red background, okay, and then the outcome variable, or the dependent variable that they were looking at, was the woman's attractiveness on a scale from 1 to 9. Okay, so think for just a moment, which of the inferential statistical tests that we've talked about would be appropriate for this experiment? Okay, so again, we had one group of men see a picture of a woman on a white background, and one group of men see a picture of the same woman on a red background. Okay, and the dependent variable was perceived attractiveness on an interval scale. So considering everything, all of the parameters of that study, which test would we conduct to analyze our results? Okay, so just think about that for a moment. Okay, so this is an excerpt from the actual study, okay? And if you guessed independent samples t-test, you are correct. So they used an independent samples t-test to examine the effect of color condition, red versus white, on perceived attractiveness. and the analysis revealed a significant effect of color. Okay? As displayed in the figure, participants in the red condition rated the target woman as more attractive than did those in the white condition. Okay? And we know, based on that p-value, right, we know that it's less than 0.01, okay, which means this difference in perceived attractiveness across the red photo condition and the white photo condition was significant. Okay? So let's consider how we might take the results of that experiment and turn it into a factorial ANOVA, right? So the previous example I gave you was a one-way test, okay? And it was an independent t-test because there were two levels, okay? But let's consider a second variable, independent variable, that might be interesting, right? So let's suppose they conduct the same experiment, except that they also compare the gender of the rater, okay? So gender of the rater is one independent variable, and photo color is another, okay? So just like in the previous slide, okay, we can use that helpful notation, right? So we have two independent variables, which means we need two different numbers, okay? And we have, for IV1, which is photo color, we have two levels, white versus red. And for the gender condition, we have male versus female, or the sex of the rater. We have male versus female. Okay? So that would give us a 2 by 2 factorial design. Okay? And just like before, right, we have three different things that we're testing for. One thing that we're testing for is the main effect of photo, okay? So what we're testing for when we look for a main effect of photo is, regardless of gender, is the mean attractiveness for what the white photo different than the mean attractiveness score for the red photo, right? So that's a main effect of photo. Okay, but we can also look for a main effect of sex. So regardless of photo color, is the mean attractiveness rating given by males different than the mean attractiveness rating given by females? Okay, so those are 2 out of 3 is our main effects, where we look at the effect of one IV while ignoring the effects of another IV. Okay? And now we get to that third one, where we test to see if the effect of photo color depends on the sex of the rater, right? So it's possible, we know that men rate the red photo as more attractive, right? That's what we learned from the previous experiment, is that attractiveness ratings, when it's just men rating the women, are higher in the red photo condition than the white photo condition, right? But now we have the inclusion of women in our experiment, right? So maybe women like the red and the white photo the same, okay? So maybe there's no difference when women are the raters in attractiveness between the red or the white photo, or maybe women actually prefer the white photo better, okay? If either of those possibilities are true, then we have what's called an interaction, right? So an interaction says the effect of photo depends on the sex of the rater, right? So, do people like red photos better? It depends on the gender, right? Men like the red photo better, but if women like the red and white the same or have a preference for the white photo, okay, then we have an interaction. Okay, so again, what we're looking for with an interaction is, do men and women differ in terms of which photo they rate as higher in attractiveness? Okay? All right. So now we actually don't have to do any more calculations by hand. We are just going to utilize SPSS. Okay, so you guys have a tutorial this week that's actually going to go through step by step how to compute a factorial ANOVA in SPSS. But for right now, I'll just give you a quick run through. So if you are trying to conduct a factorial ANOVA in SPSS, okay, you would go to Analyze, General Linear Model, and choose Univariate. Okay, so Analyze, General Linear Model, Univariate. Okay, and then in the dependent variable, obviously you're going to put in attractiveness rating. Okay, and in the fixed factors, you're going to put our two categorical independent variables in. Okay, so you're going to put in gender of the rater and background color of the photo. Okay, and then you just hit OK. And on the next slide, we have the output from SPSS. Okay, so the first thing we're going to assess is the potential for main effects. Okay, so is there a main effect of photo color? Again, what this means is ignoring the gender variable overall. Do people differ in their attractiveness ratings between the white photo and the red photo? Okay. So what we're going to look for to evaluate this is we're first going to look at our descriptive statistics. Okay. And our descriptive statistics for the main effect of photo are going to be in the descriptive stats table under total. Okay, and that's going to give us the total means for white versus red, ignoring the gender of the rater variable. Okay, and what we see is the mean attractiveness rating, regardless of gender, was 5.96, whereas for white photos, and 6.4 for the red photos. Okay, so just eyeballing that, it seems pretty unlikely that there's there's an effect there, because those numbers are pretty close together. Okay, but if we want to check to see if that difference is significant, we're going to go to the tests of between subjects effects, and we're going to look at the color variable. Okay, and what we see there is we have, just like for the ANOVA table, we have our sum of squares, our degrees of freedom, our mean square, our F, and our p-value. Okay, so the F and the p-value are the things that we are interested in. Okay, and we see that the p-value is 0.160. Okay, and remember, the criteria for determining whether or not we have a significant effect is that the p-value is less than 0.05, right? So 0.160 is quite a bit bigger than 0.05. So there we can say that there's not a significant main effect of photo. Okay? But again, we always want to report these correctly in APA style, right? So if you were writing up these results, you would want to include your hypothesis, right? We hypothesized that uh, um, there would be a main effect of color such that the red photo was preferred over the white photo. However, the main effect of photo was not significant, right? Um, so yes, that's where you would find that information. Okay, is there a main effect of the rater, right? So again, if we want to look at the means, right, we would go to our descriptive stats table, and we would look under total again, and we would compare the total values for male versus female raters. Okay, and what we would see is that the mean between them is 6.5 versus 5.9. Okay, and if we want to see whether that's a significant difference, okay, we would go to gender in the test of between subjects effects table, okay, and that p-value is 0.07, which is close to 0.05 but not less, okay. So we would say that overall men and women rated their photos as equally attractive. Okay, and again, we would want to report the mean and standard deviation for each of our groups, as well as the F value, the degrees of freedom, and we would say that P is greater than 0.05. Okay, so lastly, all right, we would look to see if there's a gender by color interaction. Okay, so to do that, we would first compare the ratings of males in the white versus red condition and the ratings of females in the white versus red condition. Okay, and this is all in the descriptive stats table, right? So we see that for males, again, the red photo was rated as more attractive, right? Because it's 7.06 versus 5.93. Okay? But if we look at the difference in attractiveness for the white versus red photo for females, we see that it's 5.8 versus 6, right? So just eyeballing those means, right, it looks like we would have an interaction because males are clearly rating the red photo as more attractive, but the women are rating both photos as equally attractive. And in fact, if we look at that test of between subjects effects, we see that the significance value is 0.047. And 0.047 is less than 0.05, so we conclude that that interaction is significant, right? So it looks like men rated the red photo higher, but women rated both photos similarly. Okay? And then again, we report our F value with our degrees of freedom, okay? And we would say P is less than 0.05. Okay? Another way that we can assess whether we have an interaction is by looking at a graph. Okay? So it's clear that men rated the red photo much higher than the white one. But like I said, women rated the two photos as the same. Okay? And by looking at the two lines, looking at the green line um, looking at the green line versus the blue line, right? The lines are intersecting. And we know that the more parallel the lines are, the less likely it is that we will see an interaction. And in my next video, I'll show you several graphs and we'll decide together whether they suggest an interaction or not. Okay? All right. So I just want to read you an excerpt from this same article because, in fact, they did conduct this experiment. And what they saw was that there were no main effects, but there was a significant interaction. And another way that you can tell that an interaction has happened is by looking at a bar graph. Okay? So on the x-axis, we have the rater, whether they're male or female. And then on the y-axis, we have perceived attractiveness. Okay? And we see, so again, what we're looking for whenever we are looking for the presence of an interaction, okay, is we're looking to see whether the effect of one independent variable differs depending on the level of the other independent variable. Okay? So another way of saying that in the current study is to say that we are wondering if the effect of photo color depends upon the sex of the person rating the photo, right? And what we see if we look at each of those levels of sex differently, the effect of the photo changes. Okay? So if we look at the bar graph, right, for men, the mean attractiveness rating is a lot higher for the red photo than the white photo, right? If we look at those bars next to each other, right, the one representing red is a lot higher than the one representing white. But if we look in the female graph, okay, or the female level, we see that they're essentially equal to each other, right? And in fact, the white photo is rated as slightly more attractive, even though this difference is not significant. And another thing I should mention is that whenever you look at a graph and you see those bars, they're called error bars. And if the bars are overlapping with each other, that means the difference is not significant. Whereas if they're separate, if they're non-overlapping, then the difference is significant, right? So we see that mean attractiveness is significantly different between the red photo and the white photo for males, but this difference is not significant for females, right? So again, we know that the effect of photo depends upon the sex of the person rating the attractiveness of the photo. Okay? All right. So now I would like you guys to do a problem on your own. Okay? And I will have a separate video kind of walking you through the video so that you know, or walking you through the problem. Okay? But first I want you guys to try it on your own. So for those of you who don't know, a very old game that used to be quite popular is a game called Guess Who, okay? And it was essentially a mystery game where you had to guess who the person was, and you had several cards with different people on it, okay? And you would ask a series of questions to see if the person being referenced was one of those cards, basically. So you had to decide, based on this description, who am I talking about? And there was actually a lot of controversy with this game because it's very much, it does not have a lot of diversity in terms of the people on the cards, in terms of gender or race. And so there's been subsequent attempts to make it more diverse. Okay? So this experiment is looking at performance in this game, or how well children guess the correct person. Okay? And we have two groups of kids. We have younger kids who are 8 to 9 years old versus older kids who are 10 or 11 years old. And we're looking at the original version of the game that had minimal diversity referenced versus newer versions of the game that have much more diverse members of characters in the game. Okay? And essentially we're looking to see if the effect of version of the game differs according to the age of the kids that are playing it. Okay? So here is the output, the SPSS output. And what I would like you to do is I would like you to tell me if there's a main effect of age, okay? And I want you to report that in APA style. I want you to tell me if there's main effect of version of the game, and I want you to report that in APA style. And I also want you to tell me if the effect of version depends upon the age of the kids. Okay? So you're going to tell me if there's an interaction, and you're also going to sketch a graph. Okay? Using the 4 means that you have. Okay? All right, and I will have another video where I go through this problem with you. Okay? All right. So I hope you're all doing well, and I will see you in my next video.